Hi Science 10, this is our second lesson for 5.1, and the main topic is the formula acceleration is equal to velocity over time. And we start off, I'm just letting you know that in your notes, page 16 to 22 is where this lesson is about, and it's the last of our 5.1 section. So instantaneous speed is speed at any one time like you would see on a speedometer. And average speed would be, remember, we would figure that out by distance over time, as you saw in your last lesson. And that would be how you figure out the average speed or velocity. Today we're talking about acceleration though, and the acceleration is a vector quantity, meaning that we can tell what direction it's accelerating and also if it's decelerating. So accelerating will be a positive value and decelerating will be a negative value, as I put in this star here. If there's a positive, it meant it was speeding up, and a negative, it meant it was slowing down. Acceleration formula here, we should always look at final minus initial velocity. So how the velocity was at the end of your the moving of the object compared to what it was at the beginning, and how much time that took. So it's pretty easy. We are going to do velocity in meters per second, time in seconds. So your acceleration unit will be meters per second squared. I'll mention right now that if you ever do get something in kilometers per hour, remember that you just simply divide kilometers per hour by 3.6, and that will give you the answer in meters per second, so that we always use meters per second for this formula so that it goes with seconds, which will be what the time is in. And so we can stick to acceleration being measured in meters per second squared for that reason. They do mention here that there's a formula, force is equal to ma. This is on your data sheet, and you guys can try that out. Very simple. It just means that force in newtons is mass times acceleration, and sometimes they may ask you to find acceleration by doing velocity over time. And once you get the velocity divided by time to get acceleration, you guys know how to use this triangle, then you may have to take that acceleration and put it into this formula and find out whichever one they're looking for, force or mass, depending on what the question is. But I just wanted to show you how those two go together in case you get a question like that. With velocity, if it's going in constant speed, something is speeding up uniformly, they call it uniform motion. Whereas if it's changing speed, going faster and faster, like you at a stop sign and going up to 100 kilometers an hour, that would be called accelerated motion and acceleration. Whereas if you're going 100 and go slow to stop to at the stop sign again, you would be decelerating. So we've got this Rihanna's question here about 0 to 60 and 3.5 as a little opening question. And we want to look at the acceleration there, velocity over time. This question is giving you the 60 is actually in miles per hour. So we got to do this over here and make your miles per hour, the American unit, into meters per second. So if it's 60 miles per hour, we just multiplied by 4.447 meters per second, which is then going to do a conversion for you, put it over the time, and your answer is 7.7 meters per second squared. So that's how you're finding out the I'll just take this one out here because I have it below. That's how you find out the answer to that question. It's just velocity over time. Okay, so this one is just showing you that some object going north is accelerating and it keeps accelerating 10 meters per second And so they would consider this to be velocity changing, like continually getting faster. So you are seeing an acceleration there. And you would call that constant acceleration because it continues every second to accelerate by 10 meters per second. So you'd say that's a constant acceleration. That is not the same as constant velocity, because constant velocity would be where the velocity is the same all over time. So whether it's 2, 4, 6, 8 seconds, it continues to be going at the same velocity. That would be constant velocity. Constant acceleration, it means that it's accelerating by the same amount, 10 meters per second, every second. So that's just showing you that that's a different thing. In the next question, they're just saying, what would it look like if you were accelerating constantly? And that would be this question here. It would end up being a straight line if you have constant acceleration. Whereas if you are speeding up, it would look like this. So you can see that it's going to be a curved line if it's the speeding up. And of course, if you had something where it was slowing down, it would curve the other way. So this is a speed up type of non-constant acceleration. This one is a slow down type of graph, and also non-constant acceleration. Okay, so just practicing the change in velocity over change in time. We've got some examples here, and they're all fairly easy, really. You're going to make sure that you're doing final minus initial. So the final minus the initial velocity, 20 minus 10 over the change in time of 5 seconds. And you get an answer of 2.0 meters per second squared. Remember, acceleration is meters per second squared because velocity is in meters per second, time is in seconds, so that makes it meters per second square. The cheetah says it's going north, so remember to put north in our answer to keep it a vector quantity. Here, the easy way to work with kilometers per hour, what I mentioned earlier, is just divide by 3.6, and that will make it in meters per second so that you can start your question. 96 kilometers per hour divided by 3.6 is 26.6 right here, divided by the seconds, which is 3.0 seconds, and you get your answer for the cheetah, and it's 8.9 meters per second squared. Don't forget to write north because it was said that in the question. So really the easy thing about this is just that there's this simple way to get your meters per second, and just make sure then when you're doing velocity over time, your velocity is in meters per second so that it works with the seconds, because your acceleration is meters per second squared. So you've always got to convert that kilometers per hour. This Larry McBride question, it shows you what you'd have to do if you were going to convert your kilometers per hour, multiplying by 1 kilometer has 1,000 meters, 1 hour has 3,600 seconds, but you don't have to do that if you are just dividing by 3.6. So you take your kilometers per hour, divide by 3.6, and you're going to get your meters per second to use in your question. So we don't have to do all that. We just do take the 10 point, sorry, it was supposed to be 105.05. I just forgot to write it in properly. Okay, so you take your 105.06 meters per second that you calculated, and you are going to divide that by your time in seconds, and your final answer is 18.1. Okay, I just want to make a point of just saying that your 105.06 over here, 105.06. What we were subtracting for initial velocity was that it started at 0. So that's why it's still the same number. We did do the subtraction. It's just that your initial velocity was 0 because it was starting from stop and moving. Okay. The dog question, he skids to a stop because he was skateboarding. Must be a pretty tricky little guy. And so because his initial was that he was going at 13 kilometers an hour and he is stopping, this is the V2, your final velocity, 0 minus 13 over 3 seconds gives you a negative value, and don't be afraid of that. It just means that he was decelerating or slowing down. So your answer will be minus 4 meters per second square. We use 1 sig dig because 3 is just 1 sig dig. If it was 3.0, then you could use the 4.3. But I'm just pointing out that if it was going, it was moving and stopped, he's decelerating. So that's going to show up as a negative value. Okay, the picture, last one for this section. I just drew a little picture here to show you that he's throwing the ball at 47 meters per second to the batter, but then the batter hits it back at 31 meters per second going the other way. So we've got to put a negative sign because it's going the other direction. Remember, you're going backwards. It's going to be indicated with a negative. So your V2 here is negative 31, and then you minus the V1, which is 47 that the pitcher threw it at. So minus 31 minus 47 ends up being a negative value divided by 0.92, and that's how you get a negative 85 meters per second squared because of having to use the negative of going the other direction. So there you go. I will post answers to page 92 if you'd like to try a couple there. You'll see those posted. But we're just going to finish off with talking about what the graphs look like. If you are, and this is something we've already talked about a little bit, and we were saying that if the thing is changing, accelerating, like speeding up, it'll be a graph that's swooping upwards. If it is slowing down, it would be a graph that's swooping downwards. If it is in constant acceleration, it's going to be a velocity that keeps going up in a straight line. So this is what this page shows us again, that this is the exact same object, but you have to pay attention to what the two variables are there on the side of the graph. This one says here's the position and versus over time. So this one is getting further and further away over time in a swooping up fashion. So that means that it is constantly accelerating. This second graph, though, is the same object. It's just showing you now how fast it's going. So this is velocity. So it's going faster and faster over time. And if it's velocity time, going faster, faster, it is a straight line. If it is the position over time and it's speeding up, it'll be a curved line. So you guys can sketch these two and just remember that this one position is like distance basically, but the distance times graph if you're speeding up is curved. The velocity time graph if you're speeding up is a straight line, but it still shows you're speeding up because as you can see, you're going 20 meters per second, then 40, then 50, so you are speeding up. And it would be a straight line just because it's showing you velocity going up. Okay, if it's going a very constant velocity, I mentioned that before, so if it's going 100 kilometers an hour the whole time because you're in cruise control, that would be called uniform motion. If velocity time is a straight line, that's uniform motion. But if it's accelerating at all, that would be called non-uniform motion. And that would be the slowing down or speeding up type graph. Okay. So these examples are showing you to be careful of what the side of your graph is showing you. These are showing you the distance over time. This guy is quickly curving up, so it's going to be showing that it's going faster, and that's positive acceleration, whereas this one is the curve is going the other way, so it is slowing down. So this guy is accelerating, and this guy is decelerating or slowing down. The next example is now a velocity time graph, and so this is how fast it's going over time, and this one is obviously accelerating because it's going faster and faster over time. As you go down time, he's going faster. For this one, from time 0 over time, he's going slower and slower. So this guy on the right is decelerating to a stop because he ended up being at 0 velocity, which means he stopped. Okay. Last thing is that if you have any questions talking about acceleration due to gravity, falling to the earth, they have calculated that things that fall to the earth are pulled with 9.1 meters per second square of gravitational pull. So acceleration due to gravity is this value, and that is a value that you should memorize. I do not see that they've put it on the data sheet, so that's just one of those oh, hang on, I do see it on the data sheet. Okay, so your data sheet for Science 10 would have this value that acceleration due to gravity is 9.81 meters per second square, in case you have any questions that have that value needed. There's a few other practice questions, page 196, that I will post answers to. So for this section in this lesson, your questions will come from the textbook, and I've been photographing those and providing answers to those. Even if you don't have your book, you can try some of them out. Thanks for hanging in there, guys, for our